Hi everyone, and welcome to this video on section 5.10. I should go back up here and show you that. Improper integrals. So in this section we're going to be overviewing this idea of an improper integral. And so there's two types to it, which you can read through here. We're going to go over both of these. So let's just jump down to the definition and get started. Okay, so the first one here, A, is an improper integral where we are going to let one of the limits, so see how there's a t here, we're going to let that limit go to infinity. So in this first one, we're letting a limit to infinity. One of these limits is infinity. Now, it could be the top limit, it can be the bottom limit, and I can go to negative infinity. Right? So it doesn't not just infinity, could go to negative. I could have a limit where I set up an example here where I go to infinity as the top bound and negative infinity as the bottom. All right, so you should stop here and say, wait, so far all we've done, these limits here that we go to, the top and bottom bounds, they've been numbers. Like I plug these in, right, when I do the antiderivative. We've never talked about anything like infinity. Infinity is not a number. So this is going to be a very, very, very common occurrence in Calc 1, Calc 2, Calc 3, all the calcs, right? Because you've already seen it happen. Whenever we start to talk about anything dealing with infinity, we usually have to use a limit. So you want to get something infinitely small. You want to make something infinitely big. You want to do something an infinite number of times. Over and over again, we've dealt with that by doing a limit. And so here's what we do, and I really do think that once you think about this a little bit, it does make sense that we would do this. If we have a function here, and I'll just draw a little quick picture. Let's say I have some function here, right? Okay, and it goes on forever. This function goes on forever. Well, let's pretend that a is right here. Okay, so the integral from a to t. For every number t greater than or equal to a. What am I saying here? When I put this infinity here, what I'm saying is I want to try to talk about the area under this curve as I get bigger and bigger and bigger and bigger for my second bound here. So the way that you can think about this is, what's an infinite integral here, right? What does this mean? Well, it means I do this process. I say, okay, let's let b be right here. Now do this integral, a to b f of x dx. And check out what this is. Right? This is going to be some number we can get. Maybe we can get the actual formula and the antiderivative. Maybe we use approximation. Either way, based on the way this picture looks, I can get this. Okay, so it's like, all right, whatever this number is, write it down. So we write down that number. Then it's like, okay, well, try going out now to like this one. We'll call this C. Now I want you to get all of this area. And again, what is that? That's the integral from a to c, f of x dx. And that's some number, we'll call that C. It's a different number. It's bigger in this case. So you write that down. So currently what we would have through this process is we'd have this list, this first number, and then we'd have comma this second number that was with C. We'll call this first one number B, just so you know where it comes from. And, well, what's the process? Okay, well, I want to go to infinity. I want to keep going. So then we get a new number, D. And then we say, okay, well, what about this area, right? Like, what's happening here? And then so we have another list, or another element in our list. And what we do is we keep doing that, and we ask the question, what's happening as this D, this B, this C, this D is getting bigger, further to the right? Is this list, approaching something, this list of areas? Am I approaching something here? Or am I just picking up a big chunk of area each time, and so that the total area under the curve is going to be infinity. And that's really the two scenarios we're going to have to think about. So scenario one is I'm going to keep going out to the right and picking up more area, decent sized chunks of area. We'll talk about that in a second, that idea decent size. So you'll see in a second. But we're picking up more and more and more. And so as I keep adding in more area, this list of numbers is getting bigger, bigger, bigger. That would be an infinite limit, right? The limit here would equal infinity. Or actually, as I get bigger here, it seems like I'm adding less and less and less area each time. Smaller and smaller and smaller chunks. And if that's the case, it can happen that as I add up all this area, as I go through here, I actually reach some bound. Or I'll never reach it because it's a limit and I'm going to infinity, but it's bounded, which I know sounds crazy because your first glance, looking at something like that, you'd say, but you're getting bigger each time. But, there are functions that have horizontal asymptotes, right? That increase, but they just can't quite ever get past that asymptote. We've seen that. So it shouldn't be too crazy to think then that there could be this way to add up area where you're adding smaller and smaller and smaller. So this list of numbers is getting bigger, right? But it's somehow capped. So if you think about the function having a horizontal asymptote, then hopefully it's not too hard to see that this could also have that same kind of functionality, as I could add in more area as I go, but I'm somehow bounded in the top amount of area I can have. So, there is this third kind of weird one, but for the most part, those are going to be the two scenarios. Either I'm adding up too much area as I go and this list just gets bigger and bigger and bigger, unbounded, or I have a function where I'm adding up smaller and smaller, and the pieces are so small that I'm adding up that the total big area as I go out forever is actually capped. Which again sounds weird, but is something that we can show is true using the limit. So how do we attack this problem? Well, again, like we noticed, this is not a number. So I can't just go antiderivative big F of infinity. No, it's not a number. You can't just plug it into a function. But what you can do is, if you can solve this integral using an antiderivative and then take the limit. So just to show you kind of in symbols what that looks like, the most common thing that we will see is we can do this process. Limit as t goes to infinity of, and then we'll take the antiderivative, plug in the bounds, right? And then we will take this limit, right, which is just a Calc 1 problem. So if you think about it this way, this is not actually anything crazy. This problem is block this out. I'm putting my hand over the screen. Can you tell? Of course not. So block this out. T, just treat it like it's a regular old number. Do the antiderivative, big F, plug in your bounds, and then once you've done that, now this switches to a Calc 1 problem where you have to now apply the limit. So you could think of it that way, and then it's like, oh, it's not really anything too new. It's just I'm doing a Calc 2 thing I've learned recently plus a Calc 1 thing. So it's a two-step problem now. That's it. That's really all that it's going to come down to. So in B, it's just doing the same thing but for going to negative infinity, which hopefully it's not too bad to see. The setup is very similar. We just have to replace this negative infinity with a dummy variable, t, that we let approach that. So this is just saying same thing as the picture above, just go a little bit further left. Okay, do the integral and see what you get. Okay, go a little further left. Go a little further left. Go a little further left. Right? So we've got some more terminology here. Okay. These integrals, and it's something we already kind of talked about, they're called convergent. So this is the fancy math word. Convergent if the limit exists. So what does that mean? Just kind of thinking about it. If, when you take these integrals, you end up getting a number. That's it. The convergent means when you do the limit, as in the last step, you get an actual number. It exists, you get a number. That's it. It's divergent in all other scenarios. So you got to remember from your limits in Calc 1, what could this mean? You could get that the limit was infinity, negative infinity, or just does not exist. So there's that list of all the different ways that could happen. So convergent, if as I add up more and more area, it's capped at some number. Divergent, if any other situation happens. Okay? So the integral converges if I get that limit at the end that's a number, diverges in all other scenarios. Okay? And then what we can do is we can also deal, like I had said, with the negative infinity to infinity, and we can break that into two pieces. Okay? Assuming these are each convergent on their own. All right? So this is equal to the two pieces where A here, you could just kind of split it everywhere. The hint is take a number A that makes things as simple as possible. Often 0, not always. If you think there are going to be logs in the problem, picking something like 1 is super useful, right? 0 might not even make sense if you're going to end up with logs in your antiderivative. But still, think it through. Take a moment or two to think about a good A to pick here, okay? So there you go. Not too terrible for this type 1 integral. Okay, so let's try one out. Let me zoom out a little bit here. Okay, so this is like a real kind of crazy curveball type question to start off, but I think this does an awesome job getting us to really just like dive in. So the solution's right here, but let's just talk it out first. All right, we've got this integral. P is just a number that we're going to try to learn about. All right, you see an integral with an infinity here. Immediately, no other thoughts need to happen in your brain. Immediately. Not joking about the immediacy of this immediately. You just go limit, t goes to infinity, 1 to t, 1 over x to the p dx. Okay. You just get it out of there, turn it into something that we're used to. I can do this antiderivative, then I can do a limit. Remember, two-part problem. So get that infinity out of there. Let's get to something more we're comfortable with. Okay, so what do we say? We've got to then go through and we have to do the antiderivative of this, then take a limit. And now p, we don't know what p is. So this is a very kind of general question, but again, it's really going to work your antiderivative taking, your limit taking, all of that stuff. So let's walk through the solution of the way they have it. Okay, so first things first, what do? Boom, they set up the limit. They even make this extra nice step of moving the p up, right? Because this in the current form, it's like, oh, I don't really know what to do here, right? But we know how to deal with x to a power, right? This is nice. Nice. So that's what they do here, just move the x up. So now that it is of the form x to the minus p, we can do the antiderivative, right? So you add 1 to the top, divide by that. Whoops. Well, we'll just leave that there. That's fine. So add 1, divide, and then we've got to plug in the bounds. So let's go down here. Okay, so we plug in the bounds. You put the t in, then you put the 1 in. So the first thing they actually do, and sometimes they mess us up with this, right? So let's just write out the little quick algebra here that they did, just so it doesn't kind of mess you up too much. So they have this negative p plus 1 over negative p plus 1. Okay, so they rewrote that as 1 over negative p plus 1 times x to the minus p plus 1. Okay, and then what they did was they took this and just flipped the two. It's addition, right? So you can always flip the order. 1 over 1 minus p, x to the negative p plus 1. So that's how that came out, right? Okay, and then what they did was they brought things back to the bottom. So that's why that's back on the bottom here. Which, again, that, there's a step there algebraically. So how do I bring this to the bottom? Remember, I got to slap it with a negative to do that. So that would actually be 1 over x to the p, because negative is positive. And then this is a plus 1, right? So that becomes a minus 1. So that's the algebra that's happening there, in case that messed you up at all. So, okay, once it's in that form, you plug t in, So again, 4x, t goes in there, and then a 1 goes in, but 1 to the p minus 1 is going to be 1. So forgot to mention, right, up here, this is why I just say read everything, because sometimes I forget. We're going to assume that p is not 1, because if p is 1, then you've got the integral of 1 over x dx, which you can see from example 1 in the book is divergent. Do the antiderivative, you get the log, which remember, log just keeps getting bigger and bigger and bigger and bigger, so it's grabbing up more and more and more area as x gets bigger and bigger and bigger. I don't know why it's tasty when it's eating the area, but it is. So we're just going to get rid of that one. P is not 1. But then that still leaves us, an interesting situation here we have to think about, right? Because we're left with two scenarios that, they talk about down here. So why don't we go down and see what they say. If p is greater than 1, then p minus 1 is bigger than 0. So do an example. You read something like this, right? If you're kind of like, wow, what are they saying? Just do an example. They said p bigger than 1. Pick one. P equals 2. So then what's going to happen over here? I'm going to have 1 over t to the 2 minus 1, which is 1 over t. So that's what they're in their head. So now complete the sentence. So as t goes to infinity, so now think about this example you have in your head. As t gets really big, this is going to get really small, right? T is getting really big on the bottom, so then it's going to go to 0. So that's all they're saying here. But again, if it's hard with the p's, it's okay. You may not be used to doing examples with the abstraction here with the p. So just throw in a number that fits what they're talking about and give it a shot. Try doing the rest of what they're doing. So what ends up happening there, thinking through that, is if p is bigger than 1, right, this piece goes to 0. So let's think that out. If this goes to 0 in the limit, this goes to 0, we would be left with 1 over 1 minus p, and then over here, a negative 1, okay, which that negative 1 can get absorbed in here and go top or bottom. And what's going to happen is, what they do here is they take this negative 1, hit it with the bottom, so it becomes negative 1 plus p, which is right there. So what does this mean? I took the limit, I get a number because p is a number, right? So this is convergent. So this being a number tells me it converges. All right, what if p is less than 1? The only other scenario, right? If p is less than 1, they say p minus 1 is less than 0. Again, if it's too much abstraction right now as you're trying to learn this, pick a number. P equals negative 1. You make it not too hard, right? So, okay, if that's true, then what did we have here? To go back up to the limit we're going to do, right? It was 1 over t to the p minus 1, which is right here. So then plug in your example. 1 over t to the negative 1 minus 1, 1 over t to the negative 2. Oh, okay, it's a negative power, so that's just t squared. So now, as t goes to infinity, what does this do? Well, if t's getting big, t squared's getting even bigger. So this definitely goes to infinity. Okay, so let's go back here. This piece now, right, we'll write out the limit again just so you can see it all together. The limit as t goes to infinity of 1 over 1 minus p, 1 over, let me actually simplify a little bit since we already wrote what that was, right? We just said in our example, right, this was t squared minus 1, right? Because we did that example negative 1 here, which we could replace this p, but just ignore it for now. We just said this is going to go to infinity, right? To infinity. So a very big number minus 1 is still huge. This p is negative 1, so this is just a number. So a number times a huge number, it's huge. So this is going to diverge. And that's what they get. Woohoo! So there you go. Hopefully, that's not too terrible to do going through that. But, what do you want to grab out of this? Like, okay, we just did that example, and Mr. B had fun, and I just was fine with it. Yeah, if I can get you there, great. Well, what we just got was a huge addition to our toolbox. So I want you to really pay attention to this, because this will be crazy helpful for you later. This example we just did, what did we get out of this? We just got some new stuff for our toolbox of these integrals that gives us a way to think about new ones in the future. So in our toolbox here, what we end up getting is, if I see this and p is bigger than 1, I immediately can say converge. So things that look like this in my mind going forward are going to be convergent. P less than 1, I'm going to diverge. Going forward, if I see a p less than 1, I'm thinking divergent. And if you go look at example 1 in the book, p equals 1 also diverges. So look at that tool. Think about the crazy number of functions, technically infinite number of functions, that we just now can just immediately answer this question for. Very, very, very helpful, especially for chapter 8. So hold on to this. Make sure this is in your toolbox. Okay, so let's keep going here. All right, so this one says, let's zoom out. Determine whether each integral is convergent or divergent and evaluate those that are convergent. That just means take the limit all the way through. That's it. So when it says evaluate, it just means do the limit. So, okay, here we go. We've got this function here, right? 1 over 1 plus x, and it's in the 4th root. So stop. I told you last time, immediately limit. Okay, so immediately limit. Limit, t goes to infinity. Look at us go, 0 to t, and great. We got this going. Okay. Now stop again. Don't go anymore. Look at what you have. You've got 1 over the 4th root of 1 plus x. I'm going to rewrite this over here, so maybe you can kind of see where I'm going. 1 over 1 plus x to the 1/4. Now, this 1 here, in here, is just a shift to the function, a horizontal shift to the function 1 over x to the 1/4. So this is just shifted. Okay, shifted by 1. But wait, look at this. I just learned about this one. 1 over x to the p. Well, what is this? P, right? P equals 1/4 in this shifted example. But wait, 1/4 is less than 1, so divergent. This is going to be a divergent integral. Now we're going to go, we got to go through and do it. But still, that's the way you got to think about this. If you've got the toolbox and you can get yourself comfortable with these functions, a little more comfortable, like, yeah, this is basically just x in here, just a small shift to the function. But come on, it's basically just x. Then you can really start thinking about what you know and apply. So this is gonna be divergent. Okay, and so you can look at some graphs here and kind of see what's going to happen, right? As you could think about the function here, as x gets really, really big here, you're going to get big numbers under the 4th root, and even though the 4th root's going to become smaller, you're still going to get bigger numbers down here, which makes us smaller in the long run. So see how I'm getting smaller? But this here is actually the graph of this integral. So here, this is, which I'll call little f of x. This one here, that's f of x. This one is a new function, big F, which is the integral, right, from 0 to t, 1 over 4th root 1 plus x dx. Right, so this we'll call f of t. So what is this doing? And it's a cool picture to kind of think about and learn about. What this one's doing is each number here I plug in, and we've done this already, right? Back earlier chapter 5, I plug in, here is 10. I plug 10 into this, and I add up all of the area here from 0 to 10. And then 20. I plug 20 into this. I add up all the area from 0 to 20. Boop, 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 boop. So as t gets big here, we see that, whoa, look at this function. It's getting bigger and bigger and bigger. I think that means diverge. So my initial thought process is backed up by these pictures, or at least it seems like it. Okay? You can even then look at this table of values as, again, t gets bigger. This function is growing and growing and growing and growing, and it doesn't necessarily seem like it's really slowing down its growth much. So, again, making me think diverge. Okay? All right, so if you wanted to do this one out, let's grab it. See if we can remember as we write here. We'll do this one out. And we're going to go a little quicker here. But remember, you can just slow me down if you need it. Pause me. So again, we noticed this looked like 1 over the 4th root of just x. So that's another thing that you can be like, oh, wait a minute. That makes me think I could do a kind of quick u sub, right? So 0 to t, take your limit. These things kind of go hand in hand here. If you notice that this is like just a small change, then that just means that a u sub is going to work pretty good on this. And this is a good example to see how the u sub works with the limit. So I'll show you that too. So, okay, I think this is a u sub. U equals 1 plus x. Du is just 1 dx. So let's do the substitution. We'll start down here. Limit as t goes to infinity of, I'm going to leave the bounds for a second, 1 over u to the 4th root du. Okay, now I stopped with the bounds, right? But that's because, what? That's because I did a substitution. So again, two methods. Do this antiderivative, plug back in for x's, and your bounds stay the same. Or change the bounds right now. Just so you can see it, let's change the bounds now. So let's change the bounds. So bounds. When x equals t, u is 1 plus t. Just using this formula. When x is equal to 0, u is equal to 1. Hopefully now you're seeing the shift I'm talking about, right? It's just a shift. This idea. So okay, awesome. So we can do this. Let's do the antiderivative. If we remember what we talked about above, this is really 1 over u to the 1/4, which is, so we'll kind of move this a little scratch work, u to the negative 1/4. Add 1, divide. So limit t goes to infinity. Okay, I'm going to add 1 to this and divide. So that's u to the 3/4. And then I'm going to hit it with a 4/3. When I divide 3/4, I flip the fraction. Okay, and then my bounds are 1 and 1 plus t. Let's keep going. Let's plug in our bounds. Limit t goes to infinity. All right, plug in the 1 plus t. So this is 4/3, 1 plus t to the 3/4. I'm going to pull the 4/3 out. Minus 1 plus 1 to the 3/4. Okay. So that's limit t goes to infinity. 4/3, 1 plus t to the 3/4 minus 2 to the 3/4. And then we got to think through this limit, right? So as t gets bigger, number, who cares? Okay, in here, 1 plus a big number to the 3/4. Well, 1 plus a big number is going to be a big number. Taking it to the 3/4, still going to be a pretty big number. Minus 2 to the 3/4, who cares? That's just some small number. So this whole thing is going to get really, really big. So this is going to go to infinity, which means this is divergent. That tells me the integral is divergent, which is what we thought at the beginning. Is divergent. Woohoo! So there you go. So we looked at a table, we looked at its graph, we just looked at the form of this function and connected it to our toolbox. And then we did it out. All right, so all the different stuff you can try to do to figure these out. Okay, let's keep going. All right, next one. So here's the graph of this next one. Starts off, with this nice little kind of jump. And then as x gets bigger and bigger and bigger, because this is x, so let me label that x. And remember, this is f of x. As x gets bigger and bigger and bigger, this function's getting very small very quick. Okay? What happens here? Remember, this is the integral, right? So this is big F of t. So we have this function f of x, and we have this function f of t, which remember is just this integral, the whole integral, but from 0 to t, not infinity. And as t gets bigger here, we're increasing area, which makes sense. There's more area we're adding up as we go this way. But it does look like this is kind of flatlining, right? It looks like we might have a horizontal asymptote here, which would mean this converges. If this integral, this function defined by the integral, with a t here, as I get t bigger and bigger and bigger, if there seems to be a horizontal asymptote to that, then this is going to converge. Now, if we look at the table, look at that. It really looks like it's getting closer and closer to 0.25, 1/4. So what you're going to do from this is say, I think the answer is going to be 1/4. Now, let's show it. Now, just to kind of show you again the other intuitive idea, and I will say many, many, many times that as you get more experience, you can feel more comfortable doing what I'm about to do. But this is in no way a proof in any sense of the word, and can lead you astray if you're not very careful about it. And you get more intuition behind you with trying different problems. But with all that said, when I look at this, just to kind of give you a little kind of how am I viewing this, I look at this function and I'm like, okay, so as x gets really big, what it seems like to me is x big, the +2 doesn't do anything. So really this is going to look more like this, right? Because the +2, what's that doing? Not much. So then that's really x to the 4th, and this is 1/x cubed. So in my mind, looking at this, when x is super big, this function is probably going to look a lot like this one. But that's a p equals 3, converge, right? 1/x to the p, 3 is bigger than 1. Our toolbox says that when I do this integral all the way to infinity, this is going to converge. So I think in my head converge. The graph, the table are all making me think converge. And that's not too much work to do, just the beginning to feel it out. Now let's see what happens. So we can do this integral, 0 to infinity, x over x squared plus 2 squared. Okay, let's write out the limit. Limit as t goes to infinity of the integral from 0 to t, x over x squared plus 2 squared dx. Okay, now I'm looking at this, I see u sub, function in a function. So let's try it. U equals x squared plus 2. Du is 2x dx. Now there's no extra 2 out here, but that's okay, because I can just do du over 2 is x dx. I have x, I have dx. U will go here. We're looking good. Limit t goes to infinity. Okay, we're going to leave it boundless and just do the switchback, right? So I'll just leave the stars here because we know we need to do something again. Do the substitution. That'll be 1 over u squared. So then we end up with du over 2. Okay, and remember, 1 over u squared, a little scratch work here, is u to the negative 2. So if I do this antiderivative, I'm going to get limit as t goes to infinity, right? Add 1 and divide. So we've got the 1/2. We've got u to the negative 1. And then dividing a negative 1, well, that's not really going to do anything. That's just going to put a negative here. So I could put the negative 1 on bottom, but that just puts a negative on things. Okay, and then what do we want to do? Again, we got to plug in our bounds, but let's go back to x's first. So let's go back to x's, and then we'll update the bounds for real. So this is negative 1/2, and then we've got x squared plus 2 to the negative 1 from 0 to t. All right. Okay, so now let's plug in our bounds, but I'm going to drop this on the bottom when we do it. So I'm going to do a little algebra step as we go here. So remember, negative 1/2 can just come out. 1 over t squared plus 2 minus 1 over 0 squared plus 2. Okay? Now, what happens as I go to infinity? So take the infinity and let's get past this constant. Infinity on the bottom, squared even, is going to make the bottom really big. So this is going to go to 0. This is just a number. I end up with negative 1/2. That went to 0 minus 1/2. Negatives hit, they cancel. Half times half is 1/4. And there we go. Just as we thought. So hopefully that's not too bad. Let's keep going. All right, so let's look at example 18. So in example 18 here, you see that instead of having infinity as the top bound here, we actually have it as negative infinity here. So okay, this one's maybe a little bit trickier to see what's going on with this because we really got two functions here. And so what you can do if you're trying to just think this through like before is separate them into pieces, r and e to the r over 3. Okay, and so we want to know what happens as r goes to infinity. All right, so we can make this like a little table here. Sorry, negative infinity. Okay, well, this is just r, so negative infinity right away. But what about this one? So what's happening here? E to the negative infinity. The over 3 doesn't do anything, so we could really just think of this as e to the r. E to the negative infinity. Well, something like that, right? You just have to draw this out for yourself. Just take e to the r, and if you draw this out, you're going to get something like this. Okay, so when I say negative infinity, I mean, what happens as I go this way? Well, it looks like e to the r goes to 0 as I go left, left, left. So this is my just guess right off the bat. And so what is actually happening here? I've got this battle going on where r is trying to pull us big, 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 big. Again, the negative is negative, but in absolute value, the r is getting bigger and bigger and bigger. But this piece is trying to make us small, closer to 0, smaller, smaller, smaller. And so the question here is who's going to win? And what you can do is you can think of this in terms of, kind of the other direction, right? And what I mean by that is think of this is just r, the r-axis. If you think of this as just like a regular old function, just, like y equals r versus y equals e to the r over 3, or just e to the r. Well, we're trying to see who's stronger in the long run. If you just go to infinity instead, focus on infinity, then in the long run, and you can kind of graph this out if you want to, just to kind of see what's happening. In the long run, right, we can kind of draw this r out. In the long run, e to the r is going to get faster, much quicker than just r. This function, exponential growth, really dominates this function here, r. Like super, super dominates. So when we're trying to compare these two just in our minds, e is much stronger than r. It'll get bigger, quicker, and if it's trying to get really small and the other one's trying to get really big, our sense should be that this is going to dominate. All right, so it's going to try to get to 0 faster than this is going to try to get big, and so it's just going to keep pulling it back to 0. So when I look at this, my initial thought is when I multiply these two, their battle will be won by e, and so I think this might converge. So all of that thinking through, I think it's going to converge. Okay, so we can look at the picture of this. So this is the r-axis, and this is our function, little f of r, which is right here. Okay, now as r gets more and more to the left, the function, look at this, it's really getting close to 0. E to the r is winning in this battle. As I go here, what we can see is as we let this variable, if we want to call it t, whatever we want to do, right? Remember, we can call this big F of t is the integral from t to 6 of r e to the r over 3 dr. As t is going further and further left, I'm adding and adding and adding up more of this area here. And what it looks like is happening is that it looks like it's kind of, you know, again, horizontal asymptote possibly, just kind of, you know, flatlining. So as I go this way, it looks like it's flatlining. So that's making me think converge too. Let's go over here. Check this out. As t gets further and further negative, I'm actually reading up, right? I'm adding up this, right? It does a little weird stuff at the beginning, but then look, it looks like it's flatlining maybe around the 66 point something. So, okay, it looks like maybe this limit does converge. So all that together, I think, converge. But, you know, there's one way to figure this out. You just do it. So limit as t goes to negative infinity of the integral t to 6 r e to the r over 3 dr. All right, so we've got all these rules, but this reminds me immediately of integration by parts because I've got two functions multiplied, one of them that gets simpler if I do the derivative, the other that just kind of messes around and doesn't do anything, e. So that makes me think like, okay, let's just do integration by parts. U is r, du would be 1 dr. Okay, dv is going to be e to the r over 3, and v then will be 3, I should put my dr there, 3 e to the r over 3. Now remember, that's technically a u sub, but that rule that we had seen, when you do the antiderivative and all you've done is multiply the variable by a number, you just divide by that number, and there you go. So we got to remember, it's uv minus the integral of v du. So we'll put that up here as a reminder. uv minus the integral of v du. Practice, practice, practice this. Okay, so let's plug it in. So limit t goes to negative infinity, uv, 3r e to the r over 3, minus the integral of v du, 3 e to the r over 3 dr. Okay, so that's not too bad, but, you know, don't forget your bounds. And then remember, this is also going to be t to 6, but we'll deal with it all at once later. Okay, so do the antiderivative here. It's the same one that we just did up here. So this will be limit t goes to negative infinity, 3r e to the r over 3, t to 6, minus, and then again we just pop out the 3 again. So this is going to be minus 9 e to the r over 3, t to 6. Okay, we could just do this all together. And we can also do a little algebra here as well. So you'll see the algebra to negative infinity. So this is 3r e to the r over 3 minus 9 e to the r over 3. All of this from t to 6. And then if you want to, I mean, you don't have to, you could factor out the e to the r over 3 and the 3. So why don't we do that, just because I feel like the book also does, very commonly does stuff like this, so just so you get a little practice. So this is 3e to the r over 3, r minus 3, t to 6. Okay, and then we got to plug in. So we'll plug 6 in and we'll plug t in. And so let's do that over here. So this is limit, running out of room a little bit, to negative infinity. Okay, plug the 6 in. All right, again, we're plugging in for r. So this is 3 e to the 6 over 3 is 2. 6 minus 3 is 3. Minus, and then plug in the t. 3 e to the t over 3. And that's, of course, now we plug t in times t minus 3. Okay. So we got to do this limit. All right, the first one's just a number, so that's just that number. So that's 3e squared times 3 minus, and then we got to do this limit. Okay, so what happens? We plug this in here, the negative infinity, right? What's going to happen here? Well, e to the negative infinity, this one is trying to go to 0, and this one is trying to go to negative infinity. Okay? So, we could do a couple things here. We could do L'Hopital's rule. We have to change things around a little bit, right, to do that. But we could do L'Hopital's rule. Remember, L'Hopital's rule is if I can get this in the form 0 over 0, so L'Hopital's, or infinity over infinity, negatives don't matter, then I can do L'Hopital's. So we can do that over here. I didn't give myself enough room, but that's okay. I'm going to drop this e to the bottom so that it becomes an infinity when I look at this. So watch what happens. I'm going to redo this as negative 3, and then it's going to be t minus 3 over e to the negative t over 3. Now, when I think of doing this limit, let t go to negative infinity. What happens? We get a negative infinity up here, and what happens down here? Negative, negative is positive, right? Negative, negative is positive. E to a big, big, big number is big, big, big. Okay, awesome. We are in L'Hopital's form. The negative's fine, it doesn't matter. You just need infinity, infinity. So we're in L'Hopital's form, and remember how we do L'Hopital's? We take the derivative of this over the derivative of this. So using L'Hopital's, right, this limit as t goes to negative infinity, that we're trying here is equal to, do the derivative of the top is 1, the derivative of the bottom is negative 1/3 e to the negative t over 3. Okay? Alright, so we've got a 1 here. We do this limit. What did we just say? Negative infinity, negative, negative is positive. The bottom gets really big. This is 0. So that's all of our scratch work for the limit. So we get 0 here. Okay, so then all together, we get 9e squared. Boom. There you go. Converge. We converge to 9e squared. Done. So a lot of stuff going on there, right? A lot of stuff. Integration by parts, setting this up, doing a limit that isn't just as straightforward as the ones we've done before, needing L'Hopital's to do this. But again, each piece is something we've practiced before. You've been working hard on. You could just do it. So just piece by piece, focus on each piece at a time, which means when you're going through these problems, you got to do a good job taking away from this the steps. Set up the limit. Do the integral. Focus. Integral focus. Plug in your bounds. Okay, now switch focus. I'm doing a limit now. This is only a limit problem. It was only ever a limit problem. I'm doing the limit. I get an answer. Oh, wait, just kidding. I was doing this problem. This is the answer to this problem. So, pieces, pieces, pieces. Just do it in its pieces. All right, let's keep going. Okay, the other type of improper integral, type 2, which you don't have to memorize the type names, that's fine, is when we come across an integral that does not necessarily look special in any way, but there is a discontinuity somewhere in this, this range of values that you want to do. So somewhere between a and b, there's a discontinuity. Now, the discontinuity could be at b, right here at the top. Okay. The discontinuity could be at a. Maybe that's where the function has a discontinuity. Or there could be a discontinuity inside a to b, right? So what do I mean by that? Like if I'm going -1 to 1, so I'm doing the integral -1 to 1, then maybe 0 is a discontinuity, right? There's a vertical asymptote as an example at 0. What I do to tackle that is I can split this into two integrals at this discontinuity, and then I just treat it like two problems. There's an asymptote here, do the limit. There's an asymptote here, do the limit. It sounds like a lot more work because it's 2 problems, but look, it's still the same little f, so it's the same antiderivative. You have to only do the work once for that. So, that part isn't too bad. But this is it. There's a discontinuity somewhere. So what we're thinking of when we see this is you've got A, you've got B, and what you're doing is you're integrating some function such that, it's like maybe it's defined here, and then as it gets closer to B, you end up with something like a vertical asymptote. That's what we're talking about, all right? So like what happens to this integral from a to b of f of x? Well, we can't actually really plug in b because it's not defined. So what we have to do is the same limit idea. Get closer to b. What happens? Get closer to b. What's the area? Get closer to b. What's the area? Okay, now am I approaching anything, or does it blow up, or just not exist at all? So it's a very similar idea. We can have b as the discontinuity, like this picture. We can have a as the discontinuity, the left-hand bound, so there'd just be this picture kind of flipped, or it can be in the middle somewhere, and we can see what happens. Okay, so maybe if you're looking for a picture for this one, if this one may be a little confusing, you can just picture something like this, where we've got a, we've got b, and we've got c. So maybe you've got a function that looks like this, and then maybe a function that looks like this. So this is a discontinuity, vertical asymptote, and so if I want to figure out what this integral is, it's really 2 different ones. I got to do this one, and then I got to separately do that one. So hopefully not too terrible. All right, let's just try it and see what it looks like. So this one again, determine whether it's convergent or divergent, and if it's convergent, just don't be lazy, do the limit all the way. So okay, first thing you have to do, look at this and say, where is the issue point? Well, what could be an issue with this? It's irrational, so it's got to be the bottom. Has to be something, wrong with this function. And so it's wherever the bottom's 0. Well, the bottom is 0 when you make this 0, and x minus 6, that's not a minus, equals 0. Well, that just tells me x is 6. So this is our problem point right here. So what that means is I can't just do the antiderivative and plug in 6. It's not going to make any sense. So I've got to approach 6 and plug in values closer and closer to 6 to see what happens. How do we do that? Well, it sounds a lot like, again, a limit. So we'll do the limit as t approaches 6. Now, from which direction? 8 is good. That's to the right. So then I'm going to be approaching 6 from the right. If you ever have trouble with that, put your numbers on a number line. If this is the problem point, then okay, I'm to the right of 6, right? So then that's what I got to plug in. 8, 6, I'm coming from the right. Okay, so limit t to 8, 4 over x minus 6 cubed. And what does this look like to me? Well, I got the x minus 6. That's basically just x, right? So it's like, if I could get it to x cubed down here, I'm going to feel real good. How do I do that quickly? A u sub. U is x minus 6. du is 1 dx. Okay, so that's the limit as t goes to 6 from the right, integral. And now I did a u sub, so we'll just put stars here, because technically I'm going to u bounds, even though I haven't changed. 4 over, and then u cubed du. Okay, not too bad. We can do this antiderivative. So remember, 1 over u cubed is u to the negative 3, just as our little scratch work. Add 1, divide, u to the negative 2, divide that negative 2. So that would be 4 over negative 2, because don't forget about the 4. I've still got my limit. T goes to 6 from the right, and I've got these bounds. Okay. So again, options. Switch the bounds to u's, or just switch back into x's. We'll just switch back into x's on this one. Why not? So then this is going to, and I'll put it over here, equal to the limit as t approaches 6 from the right of negative 2, and then we've got x minus 6, took me a second, negative 2, Okay, and then what were the bounds again? Well, I've switched back to x's so I can use these, t and 8. All right, plug in. Let's see what happens. I'm actually going to take the -2 out of the limit. It's a constant, so I can pull it out. Okay, so that leaves me with 8 minus 6, -2, minus, and then I have t minus 6 to the -2. Okie dokie. So then this first piece of the limit is just a number, so I can ignore it. I mean, it's important, I can't just ignore it, but in terms of thinking this through, put it to the side. This is the one that matters. And it might be a little hard to see what happens here. So we're going to rewrite this as 1 over t minus 6 squared, right? Okay, what happens? I plug in 6. Well, it's 0, but don't think of it that way. Think of plugging in a number really close to 6. This is going to be really small. A really small number squared is even smaller. 1 over really, really small, we're going to infinity. So we've got a number, right? This is 2 to the -2, which is 1/4, minus a really huge number. So then this whole thing wants to go to -infinity. And so you got the -2 here, so really the whole thing goes to infinity. But that's not the point. The point is that this limit is going to go to infinity. So then that tells me that this diverges, because the limit is infinity. All right, so the limit here is infinity, so we're going to diverge, and then we can kind of check out what happens here, right? Here's our picture. It was like the one we drew before, and let's look at what happens. So the integral from a to 8. So we're starting at 8. Okay, 8 to 8. Well, I haven't moved. Right, 7.5, this area. Okay, that's that. Okay, now I want you to do 7 to 8. What's that area? There you go. 6.5 to 8. What's that area? Right, so 6.5 to 8. All that area, that's this one. 7.5. Then I take a step closer, 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 closer to 6, and I'm getting big. Look at big, 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 big numbers. So as I go towards 6, these numbers are going to infinity, which means we're divergent, right? And then Mathematica tells you, you plug in the integral, does not converge on 6 to 8. Boom, you're done. All right, for this next example, we've got natural log x over root x. Again, we're looking for possible discontinuities, just these problem points. And actually, 0 works double duty here. This is a vertical asymptote for log and for square root of x. It's not defined for either of these. So we got to kind of think about what to do here. Okay, well, again, we identify the point, so immediately we write this as a limit. Limit t approaches 0, again from the right, because it's a currently, right? It's that leftmost point here, so we have to approach it from the right. All right, integral t to 1, and we've got log x over root x dx. All right, so I'm looking at this, no obvious u sub here, and then I go to integration by parts, and I remember from integration by parts, right, on the set of examples we did in the lecture notes for that section, I remember that log as u was pretty good for us. That worked. So I'm thinking here I can do u equals log x. Okay, so du is 1 over x dx. So that would mean my dv is, so it's 1 over root x, which is x to the -1/2. It's going to be helpful for us. And then v is add and divide. So add 1 to this is 1/2. Divide would give me 2. Okay. So then remember, how does this work? It's uv minus the integral of v du. So that's the limit of uv. So 2x to the 1/2 ln x. And again, this is from t to 1 minus the integral t to 1 of v du. So that's v du, pointed at the wrong thing. So that's 2x to the 1/2, 1 over x dx. Now what's super nice about this, we can combo these, so our little scrap work here. X to the 1/2 times 1 over x, so there's 1x on bottom, a half on top, so that's 1 over x to the 1/2, which we'll just write it out here is x to the negative 1/2. Alright, so then this here, we can just focus on this. This is going to be the integral from t to 1 of, and we're going to put the 2 out here, x to the negative 1/2 dx. But what's super nice is we actually already did this antiderivative, so don't waste time redoing it, just copy what you have. This is going to end up being the limit as t approaches 0 from the right of 2x to the 1/2 ln x minus 2, and then what happened? We got this here. So that's times 2x to the 1/2, and all of this goes from t to 1. Okay. So this will combo to be minus 4, so we can do that, but let's just plug in. So this is going to be limit as t goes to 0 from the right of, plug 1 in everywhere. So 1 goes in here, that'll give me 2 times 1 to the 1/2, but super nice, 1 goes in here, that becomes 0. So this first piece is 0 minus 4, and then 1 in here is just 1, so there you go. Okay, then I plug t in. Nothing that nice is going to happen, but that's okay. I'm going to end up here, t goes in here, 2t to the 1/2 log t minus 4t to the 1/2. Okay, not too terrible. All right, so from here, we got to do this limit out. So we're going to separate this into two pieces. Limit as t goes to 0 from the right of negative 4 minus the limit as t goes to 0 from the right of this. Now, tricky thing here, you plug 0 in and it's like, well, I don't know, this goes to 0, this goes to 0, this is going to go to negative infinity, so it's like, I don't really know what's happening here. So why don't we factor this first? So let's take out the t to the 1/2. So, and we can actually take out a 2. So that's 2t to the 1/2 ln t minus 2. All right, now it's multiplication. Okay, that's better. So again, though, I try to plug this idea in, and this is going to go to 0. This is trying to go to 0. This one here is trying to go to negative infinity. Darn, that's not helping us because I don't know who wins in this battle. So what we have to do again is, this is going to be another L'Hopital's. We got to get 0 over 0 or infinity over infinity. And again, the negative doesn't matter with either infinity. Something of this form. Okay. So that means just taking one of these and flipping them to the bottom. This is the easier one to do. So what this is actually going to become is negative 4, because that's what this limit will be, the limit of a constant, just the constant, minus limit as t goes to 0 from the right. And then we've got ln t minus 2 over, and we'll put the 2 out here, and then we've got this on the bottom, t to the negative 1/2. Okay, so reassess. Try to go to 0. This top is going to go to negative infinity. What's going to happen here, though? Well, we know that when we tried to plug in 0, this was going to go to 0, right? So then by flipping it to the bottom, we're actually sending it to infinity. So you can do this a bunch of different ways. Thinking through like I just did, put a quick graph in. Just put this in a calculator, graph it, and see what happens when you get close to 0. You're going to see that this explodes. It gets really, really, really big. So excellent. Check. This is the right form. So we're going to apply L'Hopital's now. Negative 4 minus, and then we're going to do a L'Hopital's here. So here to here. This is the limit as t approaches 0 from the right. And we can actually take this 2 and take it outside to make it a little nicer looking. Derivative of this is 1 over t. Derivative of this is negative 1/2 t to the negative 3/2. Right? So, drop it down, subtract. All right, so we've got a little algebra to do. Negative 4 minus 2 times the limit as t goes to 0 from the right. Oh, why did I write a t there? That's silly. T goes to 0 from the right. That's a plus sign. Okay, and then the t drops, but then this t can come up. So really we've got t cubed, t to the 3/2, sorry. And then there's a t on bottom. And then this negative 1/2 can flip up to the top. So there's a -2 up here now from this flipping. Well, these cancel nice though, right? 3/2 on top, 1 on bottom leaves just a 1/2 on top. So this is going to equal, and I'm actually going to bring it all the way over here. So this is going to be -4 minus, and then I'm going to attach these two to be plus 4 times. And then I've got the limit as t goes to 0 from the right of t to the 1/2, which we already thought through this, talked through it. This is just 0, right? So this is equal to -4. Boom. So there you go. We converge. So hopefully that's not too bad. We're going to converge here. And so just to kind of recap for, a helpful thing to think about in the future is, what did we say? I think it was here, right? Right here, we had t to the 1/2 trying to go to 0 versus log trying to go to -infinity. Who's going to win? T to the power 1. Okay, so what did we have before, right? Let's try to recap real quick. Exponential beat t to a power, but t to a power beats log. So you've got that order that you can rely on now. And by beating, we mean, what do we mean, right? They're both trying to approach something. This one is going to do it faster than this one. So this gets to 0 faster than this goes to infinity, and so it's going to be able to pull it down towards 0. All right, there you go. Okay, so just you can kind of check things, what's going on here, and we see -4, right? So again, always you guys have these tools. All right, one more. So what's happening here? Well, we have to look at this and say, like, what's the problem? Well, what could be the problem here is on bottom, we could get 0. E to the x minus 1 equals 0. Well, when's that going to happen? That's when e to the x is 1, which happens when x is 0. All right, so here's an example. The problem point is actually at 0. So we can immediately rewrite this as the integral from -1 to 0, e to the x over e to the x minus 1, plus, now take me from 0 to 1. Okay, so awesome. I split on that point. All right, so then what we have to do is just, set up these limits. So limit as t approaches 0, now from the left, right? Because I have b here. I'm coming from the left of the integral from -1 to t, e to the x minus 1 dx, plus the limit as, now I'm just, it's kind of up to you how you want to do something like this. You can use t again if you want to, but really it's better to use another variable. So, because you're just going to confuse yourself as you're messing with this. Let's let s go to 0 now from the right, because they're doing different things. T is approaching from the left, s is approaching from the right. Okay, so that's 1, it's s here, e to the x over e to the x minus 1. All right, and then we just have to focus on one of these to do the antiderivative, and then just copy what we get over here. So let's just do this one because it's where my cursor is closer. Really no other reason. So okay, looking at this, it's like, oh, God, come on, I feel like I could kind of do this, but it's the silly -1 on bottom that's messing me up. But that just tells me, let me try to simplify this. Let's give a u sub a try. Because if I can just absorb this negative in to just replace with u, my life will be better. Okay, so du equals e to the x dx, and would you look at that? We got it, e to the x dx. So we can do the substitution. So we've got the integral, and I'll put the stars here. We're just going to focus on the integral for a second. This is going to be 1 over u du. We can do this. This antiderivative is natural log. Okay, and then we have star to star, our bounds. So, okay, then we can just kind of go back, right? This is going to be natural log of e to the x minus 1 from s to 1. Okay, so one thing here, we can simplify this a little bit just to because why not, it's good to think about, is we're from 0 to 1 but never hitting 0. So this is actually inside always a positive number, because e to the 0 is 1, which then you might be like, well, it's 0, but we don't ever hit 0. So this is always bigger than 1. Bigger than 1 minus 1 is always positive. So what I can actually do is drop the absolute value signs, just for convenience. It's nice to be able to do that. Now I did that work here, so that applies to this. So I get limit as t approaches 0 from the left of natural log. We'll have natural log of, what did we have? E to the x minus 1, and that is going to go from negative 1 to t. Okay, and then we'll have that plus limit as s approaches 0 from the right of natural log e to the x minus 1 from s to 1. Okay, let's keep going with this. We plug in, we'll get limit as t approaches 0 from the left, natural log of e to the t minus 1, okay, and then minus natural log of e to the 1 minus 1 plus limit s approaches 0 from the right of natural log of e to the 1 minus 1 minus natural log of e to the s minus 1. Okay, so let me just bracket these so it's clear that they're in each other's limits. So boom, boom. All right, and then we just got to kind of figure out what's going on here, right? So as I approach 0 from the left, e to the t is approaching 1, right? You could just plug in 0 to see what happens here with the e, but you'll get 1. So that means natural log, right? I'm approaching 1, which means this one here, this is approaching 1. So this is approaching 0, which means 1 minus 1 is 0. I can remember that. This is approaching 0, which means this whole thing is trying to go to negative infinity. So this piece here is trying to go to negative infinity. This is a number. It's a crazy looking number, but it's just a number. This here, this limit, again, this is just a number. This one here, again, as I approach 0, this is getting closer and closer to 1. 1 minus 1 is 0. So then this is getting closer and closer to 0 inside, which makes this, again, try to go to negative infinity. Okay, so then what I'm going to have here is this piece goes to negative infinity, this piece goes to negative infinity. Since they're both trying to go to negative infinity together, this is going to go to negative infinity. So altogether, this is going to negative infinity, and so it's going to diverge. There you go. All right, so hopefully not too terrible to try to put this all together. All right, so you can kind of see that that's happening here. As I'm getting closer to 0, the numbers are getting bigger and bigger and bigger, and we end up getting negative infinity here. Does not converge. Okay, one more thing to show you here, just a pretty useful tool, and is going to be crazy useful in Chapter 8. If you have f and g as continuous functions, such that f is always bounding g, they could be equal sometimes, but for the most part, you're picturing f is up here and g is down here. Again, they could be equal at sometimes, but f is always going to be at least equal to or on top of g. Then, if this top one converges, right, the bottom one here has to also converge. Remember this idea, if it's hard to kind of think that through, in order to converge, you need this function, right? Think of all of the examples we've seen so far. You need this function to go to 0. Right? It's got to get smaller and smaller and smaller and smaller. And it's got to do it pretty fast, right? Fast. Got to go to 0 fast. Okay, but think about this. This function's bigger than this one. So if this is going to 0 fast, well, this is going to go to 0 even faster because it's always smaller than that one. So if this one goes to 0 fast, this one's trapped below it, also going to 0 fast. Okay? So, hopefully that kind of gives you a good idea. The extra piece here is that you're bigger than 0. So the way I've set this up, you could just be like, well, this goes to 0, but this one goes like this. No, we're not going to allow that because G is always positive. So it is going to be trapped between 0 and F. So in reality, what's happening here is it is trapped between 0 and F. So if F is going to converge, so must G. Sorry, if the integral of F is going to converge, that's important. Don't make that mistake, even though I just did. Then the integral of G is going to converge. Okay? Kind of in the other way, if G diverges, which this is not necessarily the case, but just to show you. If G is going to diverge, like let's pretend G just gets bigger and bigger and bigger, so the area gets bigger and bigger and bigger. Let's just, to simplify. G is getting too big, I'm adding area, so when I do that, this is going to go to infinity. Well, if F is always above it, that forces the same thing for F. There's no way F, could converge because it's getting these bigger and bigger chunks of area, even more than G. So if G of X diverges, it's getting too big, then F being bigger, it also must diverge. This is awesome to use, okay? So definitely keep this in the back of your head. A lot of the time you're going to see me do examples where I'm like, oh, this function's kind of like this one. This gives you an actual, theorem to use something like that. It's more than just what I was doing where I was like, oh, this looks like this, right? It's, you got to do a little work. This function's bigger than this one, and therefore, boom. This function's smaller than this one, and therefore, boom. So it takes a little more work than what we were doing, but it gives you a leg to stand on with this idea. All right, so long video, lots of examples. Keep working on them. Refresh your limit knowledge if you need to. You can always ask for help with that, of course. And any help with any of the rest of these pieces, also just let me know, and I will see you in the next video.